Good morning, dear students. Our next session, that is dealing with the intensities of the spectral lines, or what are the factors which are affecting the intensity of a spectral line. Intensity means the thickness of that particular spectral line. That means we had seen that the spectral lines, it can be very bold lines, or it can be, it is a bold line, or it is a darkened line, or it can be very thin lines, isn't it? So the intensity depends upon some factors, and here we are discussing the two factors which affects the intensity. And also the first factor, or the relative intensity, depends upon the population of the energy levels. That is the first point which is affecting the intensity of the spectral line. First one, it is the population of the energy levels. Population means, as you know this normally, population means it will be dealing with the number of atoms present in that particular energy level. Okay, suppose if the number of atoms present in that particular energy level, if it is greater, what happens? The intensity of the spectral line will also be high. Okay, so that is the first factor which determines the intensity of the spectral line, that is population of the energy levels. See here, this is the ground state, the next higher energy state, next higher energy state, like that it goes on. And also suppose normally this is the ground state, and this ground state will be normally in the room temperature, and a lot of molecules, or a greater number of molecules, will be there in the ground state, isn't it? And also in the excited state, there may be some of them. Suppose 5 atoms or 5 atoms are there in the ground state, then sometimes there can be 1 or 2 atoms or molecules in the next higher energy level, isn't it? So that is the factor which determines the intensity of the spectral lines. Okay, so first one, that is the population, and the second one that affects the intensity, that is the degeneracy of the energy levels. Okay, degeneracy means degeneracy of the energy levels means degeneracy, the term itself means it will be having the same energy, isn't it? So both these factors depends on will affect the intensity of the spectral lines. Okay, and also there are some 1 or 2 points are there. The intensity of the spectral lines, it will be proportional to first factor, that is the population, that you have to go through in detail. And this population, the first factor, the intensity, it will be directly proportional to the population. So this population, it is determined by the number of molecules in the lower energy state and the number of molecules in the higher energy state. Okay, so suppose the number of molecules in the lower energy state, it is denoted by N0, and the number of molecules in the higher energy level, if it is denoted by Nj. Okay, then we can represent it as I. It is directly proportional to the I means it is the intensity. Intensity is directly proportional to the ratio of number of molecules in the higher energy state to the number of molecules in the ground state or the lower energy state. Okay, therefore we can write it as I is directly proportional to Nj by N0. That is equal to it will be equal to a Boltzmann distribution factor or Boltzmann exponential factor, and it will be equal to e raised to minus Ej divided by Kt. E raised to minus Ej divided by Kt. So this is the factor which affects the intensity, or which determines the population. So I, the intensity, it is directly proportional to Nj by N0. Nj means it is the number of molecules. It is the number of molecules in the higher energy level J, in the higher energy level J, and N0, it is the number of molecules in the lower energy level. In the lower energy level. Okay. So this is one factor. Then the second one, that is regarding the degeneracy of the energy states. Degeneracy means they will be having the same energy. That is what is the term degeneracy. And also here so many rotational energy levels are there, as you know, and all these rotational energy levels are degenerate. Okay, that means they are having the same energies. They are having the same energy. all these rotational energy levels are having the same energy. And also this, for a diatomic molecule, the degeneracy normally it is denoted by the letter Gj. Okay, Gj. And for a diatomic molecule, the degeneracy it is given by Gj is equal to 2J plus 1. Okay, for a diatomic molecule. For a diatomic molecule, Gj is equal to 2J plus 1, where J is the rotational quantum number. And if J is equal to 0, what happens? What is the value of Gj? Gj will be equal to 1, isn't it? And for J is equal to 1, what about Gj? Gj is equal to 2 into 1, 2 plus 1, 3. Then for J is equal to 2, Gj is equal to 2 into 2, 4 plus 1, 5, isn't it? So like that it goes on. So the degeneracy for a diatomic molecule, it will be depending on the rotational quantum number, or what energy level the molecule is or the atom is. Okay, atom exists. So here we are seeing two factors, population as well as degeneracy, which determines the intensity of the spectral lines. See, this topic, it is very important, the intensity of the spectral lines. And also again we can combine these two, population and degeneracy, with the intensity. So therefore we can write it as intensity. It is directly proportional to Nj by N0, and it will be equal to the two factors, that is the Boltzmann distribution, that is e raised to minus Ej divided by Kt. That is the first factor, that is population, e raised to minus Ej divided by Kt, that is population. Then what about the degeneracy? Degeneracy it is given by 2J plus 1. Okay. So the two factors, the intensity, it will be the intensity it is determined by the product of the Boltzmann exponential factor. So this is the Boltzmann exponential factor. Boltzmann exponential factor. Boltzmann exponential factor, and this term gives the degeneracy. So the intensity, it is the product of, or it is determined by the product of the Boltzmann exponential factor as well as degeneracy. So therefore we can write the equation as Nj by N0, that is equal to 2J plus 1 into e raised to minus Ej divided by Kt. K is the Boltzmann constant. Then again epsilon j, there is a relation connecting epsilon j and Ej, isn't it? Epsilon j is equal to Ej divided by Hc. Or we can say that Ej is equal to epsilon j into Hc. So therefore we can substitute for Ej as Ej into Hc, isn't it? So again write the equation Nj by N0, that is equal to 2J plus 1 into e raised to, instead of Ej we can write it as epsilon j into Hc. Epsilon j into Hc divided by Kt. Again, what is epsilon j? It is b into j plus 1. So we can write it as 2j plus 1 into e raised to, sorry, there is a negative sign there, e raised to minus bj into j plus 1, the whole divided by, sorry, into Hc, the whole divided by Kt. Okay. 2j plus, can you see this? 2j plus 1 into e raised to minus b into j plus 1 into Hc divided by Kt. Okay. So this is the formula for calculating the intensity of the spectral lines. Nj by N0 is equal to, I will be writing the equation once more. It is somewhat a mess there. So I am writing the equation again. Nj by N0, that is equal to 2j plus 1 into e raised to minus b into j plus 1 into Hc divided by Kt. Okay, so this is the intensity of the spectral lines. And also again we are plotting a graph with Nj by N0 against j. Okay, plot a graph with Nj by N0, that is the intensity against J for a rigid diatomic molecule. And also while plotting the graph, see here in the x-axis we have to plot j, and in the y-axis there will be nj by n0. And in the y-axis nj by n0, and the graph will be like this. The graph will be like this, okay. So here it is not a smooth curve, it is somewhat thickened, it is somewhat like this, okay. The area it is greater here. You have to see this much portions, okay. See, it will be somewhat a thicker graph, okay. And also here j, it is on the x-axis, and nj by n0 on the y-axis. So here this j will be maximum. See, on the x-axis we are plotting j, and this j will be maximum at a particular point. Okay, j is maximum at this particular point, and that particular point we can represent it as j max. Okay, and also this is the population distribution curve. The graph, it is the population distribution curve. Population distribution curve. And also see here from this graph we can say that the population means it is nj by n0, it will be reaching a maximum, and then what happens, it decreases along with increase in j, isn't it? At first this population increases, reaches a maximum, and then it will be decreasing. Population, it represents nj by n0, and also this particular point corresponds to j max, the maximum value corresponding to nj by n0. That is at this point the population is maximum, then it is decreasing. So correspondingly that point it is marked as j max. So this is the population distribution curve, and also there is a formula for calculating the this j max. Okay, j max, that is equal to kt divided by 2 bhc, kt divided by 2 bhc, the whole raised to half minus 1 by 2. Okay, kt divided by 2 bhc, the whole raised to half minus 1 by 2. This is the formula for calculating j maximum, where k is the Boltzmann constant, T is the temperature, B is the rotational constant, H is the Planck's constant, and C is the velocity of light. So here this intensity of the spectral lines, it is very important, and also it determines, it is determined by two factors, mainly population as well as the degeneracy, and this is a very important topic. And one more topic today we are dealing with, that is the effect of isotopic substitution. Okay. So this formula you have to by heart. J max is equal to kt divided by 2 bhc, the whole raised to half minus 1 by 2. Next is the effect of isotopic substitution. Effect of isotopic substitution. See here, we had gone through the formula for calculating moment of inertia. I is equal to mu r square, isn't it? So this moment of inertia, it will be depending on mu as well as the intermolecular distance, where mu, it is the reduced mass. Mu is the reduced mass, and mu can be calculated by the formula mu is equal to m1 m2 divided by m1 plus m2. And what is r? R is the bond length of that particular molecule. R is the bond length. And also here you have to find out whether there is any difference in the wave number if an atom, it is replaced by its corresponding isotope. Okay, we had seen this delta nu bar, isn't it? That means whether there is a shift in the wave number of that while we are substituting one of the atom with its isotope. That is, we are dealing here, that is the effect of isotopic substitution. Okay. For example, suppose consider this molecule, carbon monoxide molecule, and this carbon monoxide molecule, see here we are substituting this carbon, that is carbon 12 atom with carbon 30. Okay, C12 and C13. So these are two isotopes of carbon. So carbon 12 and carbon 13, oxygen, it has got 16. Okay. So when this isotope, when carbon 12 it is substituted by C13, is there any difference in their delta nu bar? That is what we have to find out. Okay, C12 when replaced by C13, whether there is any difference, that we have to find out. See, for that, first of all, we have to calculate the reduced mass, or we have to consider the reduced mass as well as the bond length. Okay. That is how this I will be changing, or the moment of inertia will be changing if there is any difference in mu, or there is any difference in R, the bond length of that particular molecule. And also then again one more formula is there for calculating B, isn't it? B is equal to H divided by 8 pi square IC, isn't it? B is equal to H divided by 8 pi square IC. If I is changing, what happens? B will also be B will also change. Then again, if B changes, what happens? This delta nu bar will also change, isn't it? So this is how, if an isotope is if there is any change in the isotopic substitution, or if one of the atom it is replaced by its isotope. Okay. So if we have to check whether any difference is there. So we are considering this example C12 and C13. First of all, we have to consider this one C12O16 molecule. And you have to calculate the reduced mass of this particular molecule. For C12O16, the reduced mass will be equal to 12 into 16 divided by 12 plus 16. Okay, and also in atomic mass unit, the value it is given in your textbook as 6.857 AMU. I am not converting it into kilogram. Okay, so this is the reduced mass of C12 molecule. Then the next one, when it is substituted by the isotope C13. Okay, C13. So let it be mu1 or mu. Okay, let it be mu. Okay, then the second one, let it be mu dash. So here it will be equal to mu m1 will be equal to 13, isn't it? 13 into 16 divided by 13 plus 16. So here the value it is around 7.172 AMU. Okay, this value it is around 172 AMU. See, here there is a slight difference in the reduced masses of these two molecules, isn't it? For carbon 12 as well as carbon 13. And also in both the cases, there will not be any change in bond length. R will not change if it is substituted by its isotope. Okay, so only change will be in the case of mu, isn't it? Somewhat change. That is, for C12 it is 6 point, and for C13 it is 7 point. So somewhat change in mu, so that this I will be changing. Okay, so for carbon 12 we are putting it as I, mu, etc. And for C13 we are keeping it as mu dash, then I dash, etc. Okay, for identification. Then you have to write down the formula for the rotational constant. So for the rotational constant, what is the formula? B is equal to H divided by 8 pi square IC, isn't it? B is equal to H divided by 8 pi square IC. See here, all these terms are constant. H is a constant, 8 pi square is a constant, C is a constant. Here the only variable it is I, isn't it? That means from this equation we can say that B is inversely proportional to I, isn't it? That means as I increases, B decreases, or vice versa. If B increases, I decreases. Okay, so here we had obtained two values for C12 and C13 carbon monoxides, isn't it? For C12 it is around 6 point. What about the value? It is 6.857, and for C13 it is 7.172. So for C12 the I value is lower, isn't it? For C12 the I value is lower, and again we can say that if it is like that, what about the rotational constant B for C12? It will be greater than the C13, isn't it? For C12 O16 and C13 O16, for C12 this I value it is less than C13, isn't it? That is, I is less than I dash, and again this is inversely proportional to I. Therefore, if I is less than I dash in the first case, for carbon 12 the rotational constant will be greater, since it is inversely related. So therefore for C12 this rotational constant B value it is greater than this B dash. isn't it? For C13, let it be B dash. So for C12, this value will be greater. Rotational constant value will be greater. Okay, for C12, the rotational constant value will be greater than C13. Okay, so from that we can write the formula. So from that we can reach the formula, and also this delta nu bar, normally delta nu bar, that is equal to 2b, isn't it? We had seen the formula. Delta nu bar is equal to 2b. So we can denote again as delta nu bar divided by delta nu bar dash. Delta nu bar dash means it represents the C13 molecule, and delta nu bar represents the C12 molecule. So that will be equal to 2b. That is, both of them are directly related, isn't it? Delta nu bar, it is directly related to b. So we can write it as 2b divided by 2b dash for both of them. Again, b is inversely related to I. So we can write it as I dash by I. Then again, I and mu are directly related. So we can write it as mu dash divided by mu. Okay. So therefore we can say that this isotopes will be having an effect on the rotational constant or the line spacing of that particular molecule, delta nu bar line spacing. That means for C12O16, for C12O16 the rotational constant 2b will be greater, isn't it? And for C13 it will be lesser. So the lines will be like this. That is, for C12O16 the line spacing, it will be a little bit greater. That is, this spacing, it will be greater for C12O16. In the case of C13O16, it will be somewhat lesser while comparing with that is this spacing, it will be lesser while comparing these two. Okay, so this is the effect of isotopic substitution on the molecule, and this line spacing this line spacing is different in both the cases because of the change in the, or because of the difference in their reduced masses. Okay, are you clear? This line spacing or this delta nu bar, okay, this difference we can say that this is delta nu bar, isn't it? So this delta nu bar, this difference, it is changing, or there will be difference in the case of C13 as well as C12. C12 has got a greater magnitude of delta nu bar than in the case of C13 molecule. See the difference, it has got somewhat greater difference than this one, isn't it? So that difference, it is due to the change in their reduced masses. Okay, hope you are clear with this. And also you have to do problem in this using this formula also. So both of these topics, they are very much important. That is, in the case of this intensities as well as the isotopic substitution. This isotopic substitution, it is an usually asked question, university asked question, so it will be asked anyway. You have to study it very clearly. There you have to study only the formulas. I is equal to mu r square, and you have to illustrate using this example C12, C13 and their differences in their reduced masses. Then from that you have to reach the formulas, that is B is equal to H divided by 8 pi square IC. And again, B is inversely proportional to I. Therefore, I and B are inversely related. Therefore, for C12, I is greater and also B will be greater. From that, we can write the formula delta nu bar is equal to 2B, that is the line spacing. So, delta nu bar divided by delta nu bar dash. So, this delta nu bar, it is for C12 molecule, and this delta nu bar dash, it is for C13 molecule. That is equal to 2b divided by 2b dash. So this dash terms, it is represented by, it is used to represent the isotope, that is C13. Okay, then 2b divided by 2b dash, that is equal to I dash by I, that is equal to mu dash by mu. Okay, so this is just a representation for these two. That is, you have to have an idea about the line spacing or the differences between these two cases, or the differences in their isotopic substitution. Okay, hope you are clear. If you had got any doubt, please call me. Okay, thank you. And also in our next session, we will be discussing the vibrational spectroscopy or the infrared spectroscopy. Okay, thank you.